Last class, we learned how considering the linear approximation for the susceptibility. And we also understand the Sturm-Lupus model, how much field we need to switching the uniaxial single particle. But all such approach assume the zero temperature actually. We didn't consider the final temperature. But we are living in a room temperature, so all physics must include the effect of the temperature. And especially in a magnetic switching, the temperature works a very important role. So we have to consider the thermal impact and in a magnetization switching. But as we mentioned several times, this kind of effect is not only existing switching, but the thermal effect is kind of ubiquitous. Whenever we are living in in real life. Yeah, in some extreme case, I mean, you may heard about some very low temperature. And what I'm saying is like a millikelvin something. They try to a lot of effort to reduce the temperature. Yeah, as you know, if you want to achieve the let's say a few Kelvin, that's relatively easy. If you have a liquid helium, you can easily achieve that kind of temperature. But below the Kelvin, it requires a lot of effort, more effort, and they need very specially designed instrument, and it costs a lot. But in even that kind of low temperature, still uh, the thermal effect can exist. We cannot remove the thermal effect actually, even though we reduce the temperature as much as we can low, but still the thermal effect can exist. So to understanding what is the thermal effect, we need to understand what is the meaning of the temperature, physical meaning of the temperature. So I'm gonna explain about that part. So, okay, let's start about the superparamagnetism. Yeah, we already learned about the paramagnetism. Paramagnetism itself. And what is the meaning of the super here? Okay, so what we learn is about the ferromagnetism. The definition of ferromagnetism means the magnetization direction or the spin direction is collinear in a certain range. That's kind of long-range ordering by the exchange coupling. So we already learned such kind of domain structure. But just imagine what happens if you shrink down your size of your ferromagnetic particle, and if we achieve the certain volume of the ferromagnetic material, it behave like just the paramagnetic. So look at this image curve. This is the typical image curve of the ferromagnetic materials. But this blue one, there's no hysteresis. And it looks like behave paramagnetic materials. But the big difference between the superpara and the paramagnetic material is paramagnetic material spin itself is the atomic spin is random. So they are orienting the random direction. But in a superparamagnet, they behave like a single domain. The direction of the magnetization inside of this particle are collinear. Even though we are talking about this size of a particle is order of 10 nanometer something, that means we have millions of the spins. They are pointing together. But in a real paramagnet, each spin pointing randomly. But in such small nanoparticle, without external magnetic field, the direction of the magnetization of each particle are random. But the spin direction of each particle are collinear. That's a big difference. That's why we have a order of magnitude of the ferromagnetic material for the superpara. So empirically, superparamagnetic means if we have a ferromagnetic material with a small volume size, then the direction of the magnetization is random for each particle. So overall behavior of this small particle looks like a paramagnet, but the saturation magnetization of this material is ferromagnetic, so it's much larger than paramagnetic material. So this is a big difference. So that's the general behavior of the materials. If we consider the particle size, the nanoparticle diameter, when we shrink down the particle size, usually the there is from the coercivity is getting larger and larger, because when we shrink down the nanoparticle, the volume of the ferromagnetic material, as you already know, the coercivity is determined not only the ion spin energy, but if you have some nucleation point, once the part of the sample is nucleate, the reverse domain, and the domain one is propagate and eventually obtain the switching. But in a smaller size of the ferrotic substance, there's no chance of such kind of nucleation part. So actually less chance for smaller sample. So that's why the coercivity is increased. And even though when we reach a certain volume, now the ferrite material no more prefer the multi-domain state. Instead of them, they prefer the single domain state. So that's the single domain region. So when shrink down the size of the nanoparticle more, the coercivity is decreased again for the single domain. And when we reach the certain size of the nanoparticle, the coercivity is almost zero, actually. Reach the kind of a constant value. There is no more size dependent, but actually, as you see in this graph, the coercivity of the superpara is almost zero. So it looks like extremely soft materials. But the difference is for the soft material, has very sharp image curve. With the small field, they can easily saturate. But superpara material, they require a certain number of certain size of the external field to saturate the total magnetization. Okay, so this photo shows some kind of nanoparticle. They behave. This is kind of superparamagnetic particles. So there are many applications of the superparamagnetic materials. I'm gonna explain it later. But in viewpoint of the memory application or the information application, superparamagnetic is very kind of limit. So look at this. Any kind of magnetic strategy, what we have to do is we should assign the direction of magnetization, and they should stay at that point for a long time. That's what we call retention time. And for example, this is the surface of the hard disk drive, and this small area is each grain, and this white boundary is kind of the phase segregation between each grains, and each grain are very weakly coupled to the next grain. If we have this grain and this grain, we have some grain boundary, and this grain boundary has a little bit different composition because of the some treatment of this material. This grain boundary has a more volume of the non-magnetic material. So the exchange coupling between these two grains are actually very weak. So they behave like the single particle for each grain. That's why you can making such kind of a region define some up domain or down domain. But look at this. If you want more fine information, if you want to store more fine information, what you have to do is you should reduce the grain size. If you make the smaller grain, and you can write down more regular pattern, so you can obtain the more fine bit for hard disk drive. Okay. So look at this. This is the 15 nanometer. So size of this grain is order of 10 nanometer something. Okay, please keep in mind. And this graph shows some kind of areal density as a function of the time. And this is the log scale. I already showed such kind of graph in the beginning of this class. And the areal density is proportional to the capacity of the hard disk drive. So there is a lot of progress, as you see here, from to here. It's about let's say order of 4 magnitude is 10,000 times larger, getting larger. It takes about 30 or something. And this area here, the increasement is very, very rapid. But here they are became the slowdown. The one reason is the superparamagnetic effect is the kind of limitation of the storage media. As I said, we want to reduce the grain size. But if the grain size is getting smaller and smaller, then as you see here, the we will encounter superparameter limit. And superparameter limit means the magnetic direction is very easily switched by the thermal energy. So this is the kind of limitation of the nature, the magnetic materials. But actually, this is not all magnetic materials. Any kind of energy barrier, if you have a certain energy barrier, and if the barrier side is comparable with the thermal energy, then they can easily switching between these two states. So this kind of physics is always existing, any kind of energy barrier. So this kind of a superparameter limit is very difficult, important in a hard disk drive and the memory application also. So to reduce this, overcome this idea, this limitation, what is the approach? What kind of approach is? There are three kind of approach in a hard disk drive. The easiest way is we make the high energy materials. This sounds very easy. If you make the hard enough material, we can reduce more size. We can overcome the superconductor limit. I'm going to explain the mathematically a little later. But anyway, but if you have a high energy material, what's the problem is we need more energy to write the information. Yeah, this kind of trade-off is always existing any kind of engineering problem. For example, nowadays the battery is very hard issue. What is the hard issue in a battery? One is the capacity of the energy, the stored energy, and is the charging time. So that means if you have the charging mechanism is we make some charge from one state to the other state, and they should be stored here safely. That means we need a higher barrier. That's the related to the stability. But that requires more time to charging the charge to the storage position. So reduce the time. The charging time means we need lower this energy barrier, at least during this charging time, and they should be recovered when we store the energy. But that means there's a weak point of this kind of barrier. So actually, there are many tries to recover overcome this kind of problems. You know, nowadays the charging time is getting faster and faster, but they require higher voltage, right? The higher voltage means the required energy barrier is high, but they by applying the higher voltage they overcome such problems. But that means the battery is getting unstable, or the lifetime of battery is getting getting worse. That kind of trade-off is really difficult to overcome by the engineering because it's kind of a physical limit. Okay. And the other way is they introduce some patterning or the heat assist the magnetic recording means the heat assist means the coercivity or the ionospheric energy is also temperature function of temperature. So when they give us some heat, the energy barrier is getting lower. So when we give a heat, the energy barrier is lower, so we can easily switching. But when we remove the heat, the energy barrier is recovered again, then they are stable. But this kind of approach can be applied any kind of storage media, but the give additional heat means it requires more energy and it's usually slower dynamics. So this is the not very ideal approach, but nowadays the hard disk drive industry is trying to making this heat assist multi-leveling technology. Otherwise, we can overcome the limitation. Okay, so in STT-MNAM also, such kind of problem is very important. So we're gonna talk about that. So let's back to the physics of the summer switching. We are talking about some kind of memory, especially digital memory, means we have a two stable energy state. In a magnetism, we call this is the spin up, spin down state. So without external magnetic field, usually they have the same energy. It's kind of local energy minimum. So even though there is some thermal agitation, they are moving around this ground state and vibrate around here with the certain frequency, which one is we learn. But to overcome this energy barrier, we need certain amount of the energy, external energy. As we already learned, by the external magnetic field, we can reduce this energy barrier by changing the potential shape by the external magnetic field. Spin transfer torque, we didn't touch this energy barrier, but we can excite the spins, spin motion, and finally, there is some chance they can switching to the other local state. Okay. So this energy barrier, let's say EB, then this is the purely quantum mechanical consequence. If in a classical physics, if we don't have large enough energy, we cannot go to here. But in a quantum mechanics, there is a non-zero probability they can tunneling from here to here. And this tunneling probability can be occurred at a certain time, tau. And here, this is the exponential term. And this barrier divided by, this is the thermal energy. So this barrier is larger than thermal energy. I mean, the barrier is much larger than thermal energy. This number is usually very high, very, very high. Let's say exponential, maybe, let's say 100, give a really, really huge number. And this F0 is called the attempt frequency. The physical meaning of attempt frequency is how frequently this event can be occurred. So typically, in a magnetic material, this attempt frequency is related to the phonon frequency. So they have an order of gigahertz. So it's 10 to 9. So if we multiply 10 to, let's say, minus 9, sorry, this is the minus here, plus 9. We have a 1 sec, means if we have this number is 10 to 9, then the magnetization switching can be occurred within 1 sec. Okay. So for the data storage, how many times we need to guarantee? Yeah, usually if you store some information in your storage media, like your cell phone or hard disk drive, then you assume your data can remain for infinite time. But that is not true. Any kind of storage media has their lifetime. That's we call the retention time. So at least we need 10 years. Maybe 10 years is fine. If you store some important thing in your hard disk drive, and after 10 years, if you cannot read it, maybe you cannot complain to the company. Because if you didn't touch this kind of information for 10 years, means it's not important information. But really, really important data needs more frequent backup. Okay. So we already mentioned that the delta, the thermal stability, last class, it must be 60 something. If you insert this number to here, exponential 60 something, multiply 10 to minus 9, it gives a 10 year. So I don't know, I don't remember its exact number, but it's order of 40 or 60. It depends on the details of the application. But any data storage guarantees only around 10 year or maybe 20 year something. Yeah, frankly speaking, if you found 10-year-old hard disk drive, it's not easy to connect this kind of old hard disk drive in your modern computer. All connection is already changed. That's the maybe more difficult part. Okay, there is one more joke. Long time ago, all document is stored in a paper, right? What's the lifetime of the paper? Actually, that's the longest one. If you store the paper very well conditioned, then you can keep your data, your information more than 100 years. But if you transfer this data to the, okay, for example, in a school, they store the all information of their student in a paper long time ago. But after a certain time, they transfer this paper to the CD-ROM. But CD-ROM is actually very weak information storage media. The lifetime of the writing CD, I mean the music CD, which one is made by the mechanical way. They make some stamp and they make a mechanical some music CD they made by certain mechanical stamps. So they change the mechanical structure. But the CD write by the computer, they make kind of the thermal heating of the local area, and the chemical property of this special material is changed. Actually, they changed from the crystal to amorphous. So after a long time, all amorphous got the crystallized. So they're gonna lose the information. So if you store your important information in your CD, it's not easy recover full data from your CD after 10 years. But the reality is all this thing happens probability. Okay, all this thing happens to probability only. So if you store just one bit, then there is some chance of the switching this one bit to reverse direction is, let's say, 10 years something. But all bit stored information, let's say 1 GB, is kind of independent probability. So you may lose one more bit in your CD, but the other part will be fine. So for example, the image of the data, let's say if you store some photo, but one bit error in a photo is not very important. Maybe the change of the 1 pixel, right? Maybe your hair is changed from black to white after 10 years, only 1 pixel. That's nothing. Nobody can find it. But how about the financial information? If the sign or one digit of the your financial balance is changed, this is really serious one. So storing this recording CD is very, very harmful actually. But now, fortunately, nowadays nobody use CD anymore, so it's not a big deal. But about 10 years ago, maybe 15 years ago, something, CD is kind of the major storage of the information. So when I met some teacher, I emphasized this: you cannot believe the CD is very dangerous one, and they guarantee certain storing time, but that kind of time is assume the proper temperature and the proper humidity. But usually people store the CD-ROM in your desk drawer, and they are a lot of heat around by the heater or sunshine. And there are very easy chance to lose your information. If you want to erase your CD-ROM, the writing CD-ROM, the easiest way is put it in the some the UV cleaner in a kitchen. In a kitchen there is some kind of a box with some UV to clean your top or some spoons and some things. There is some kind of UV. So UV easily destroy the stored information in a CD. Okay. So anyway, so this equation plays very important role in many thermal related phenomena. Okay. So let's think about why this can be happens. As I mentioned in the beginning of this lecture, we are living in a final temperature, especially in a room temperature. Room temperature is, do you think is a high temperature or low temperature? Room temperature is. Yeah. As I mentioned, when we talking about some certain amount of the quantity in physics, always we think of the relative. Yeah, room temperature is much higher than, let's say, the 5 Kelvin or 4 Kelvin. But compared to really, really high temperature, like temperature of the sun, it's low temperature. But we are living, if you think of the biosystem, very rare case, the biosystem can survive more than 50 Kelvin or something. For example, people cannot survive at kind of temperature. So, when we talking about the magnetism, we always think about the Curie temperature. If we more than Curie temperature, we lost the magnetic property. All magnetic properties disappeared. So we usually the Curie temperature of the ferromagnetic material is much higher than room temperature. But still, room temperature is higher than the 0 Kelvin. So we need a finite temperature effect. Okay. So maybe you heard about the thermal agitation. Means kind of a random thermal field. Why this happens? Okay, to understand this one, what is the meaning of the temperature? Have can you explain what is the temperature, the physical meaning? Yeah. Actually, that is not easy one. Yeah. Is there anyone can explain what is the temperature in physics? Okay, so let me ask a more simple question. If you have a vacuum, there is nothing. Only one electron exists. Can we define the temperature? Yeah, temperature is related to kind of ensemble average. So if you have only one particle or two particles, you cannot make a meaningful ensemble average. But if you have a certain number of particle system, then the temperature means kind of the kinetic energy, average of the kinetic energy is particles. So the room temperature means in this air we have a lot of molecules with the oxygen and nitrogen. They are moving randomly, right? And their average velocity we have a certain number. And if you convert it to unit of the Kelvin, that's the temperature. Okay. So in an electron system in a solid state, we have some certain motion like a vibration of the phonons, the phonon or the molecules or maybe ions. And this vibration velocity is related with the temperature. Actually, the temperature, this is the thermal energy, is related with the kinetic energy of this particle. Hmm. 또 안 되네. 오케이. We have a certain relation. Actually, there's some more details of the question. But anyway, important thing is mv square is proportional to the temperature. So it means in the same temperature, the v square is inversely proportional to the mass. Okay, so the velocity of the electron is much faster than the ions because it's much the mass of the electron is at least 1,000 times smaller than the ion, right? 1,000 times or 10,000 times something. So in this kind of temperature means, so final temperature means all particles involving this system are moving. Okay. So, and this motion is purely random. Purely random. So we can obtain kind of the thermal field from this fluctuation dissipation theorem. And this Fick noise means if we have an effective field by the definition from the external magnetic field or electric field and Zeeman field, and always we have a small h here defined by the thermal field. So the mathematical property of this small field h, the thermal field h, is the average value for the time and the space must be zero because it's random, right? This symbol means the ensemble average. And this part is easy to understand. The average is zero. It's very easy to understand. And what is this meaning? This is kind of correlation. Means the thermal field at certain site I and J with certain position R and R prime, T and T prime, the ensemble average is given by this expression. Here in the right-hand side, we have a certain physical parameters. All physical parameter is familiar with you, right? The alpha, KBT, gamma, mu zero, square, ms. So we're going to discuss about the physical meaning of this one little bit. But what's the meaning of this delta function? You know the mathematical meaning of delta function, right? So according to this delta function, this equation is always zero, except the I is the same to the J and T is same to the T prime and R is same to the R prime. Otherwise, it's zero because of delta function. So that means if this one and this one is not the same, this means they are same. Then the ensemble average is non-zero, but otherwise it's zero. So they are totally non-correlated. So this side, the thermal field H, and the other side, thermal field H, in a certain time and position, they are totally uncorrelated. So, for example, in a spin, if we have a certain spin here, one side, and the other side, spin direction is related with this one, because there is some coupling. So this totally non-correlation means there's no coupling. So the correlation is kind of measurement of the strength of the coupling. If there very strong coupling means if one is determined, the other one is determined, right? If it is strongly coupled. So in that case, this correlation give a very large number. So this equation means thermal field is purely random, and if we have a certain thermal field at this point and next point, thermal field is totally independent with this previous one. And also, if we think about in the same point, if we have a certain field at a certain time, in the next time, their direction and the size is totally non-coordinated. So they are pointing any direction and any magnitude. That's the physical meaning of these two equations. And that's the result of the precession dissipation theorem in statistical physics. Okay. So I believe now students got some feeling of the physical meaning of these three delta functions. And what's this meaning? This is the magnitude of the scale of the field. So this field can be described by this way. Okay. Here, the small h is, as I said, a thermal field. And if you take a look this one, this part is actually same to this one. So why we take the square root and we divide by delta v, delta t. Okay, if we believe this equation, what is the unit of the left-hand side? Physical unit. More simple question. What's the physical unit of this h? ensemble average of h. This should be unit of field. And how about this? It should be square of the field. Means the right-hand side is the unit of the square of the field. It's very it's not easy to not difficult to understand. And many students forget about the unit of the delta function. Many students confuse the delta function is dimensionless, but that is not true. If you multiply this kind of delta function by the taking integral with some function f of t, we obtain t prime, right? So that means this is the dimensionless. Delta function multiply this integrand is the dimensionless. So that means delta function is for time, they have a inverse of the time dimension. Is okay? So we need this one, give a delta t, and this one is corresponding the volume. So we have a delta v. Okay. Okay, so now the left-hand side, the h square, and this is the 1 over delta t, 1 over delta v. And this delta is just a cycle, so it's dimensionless. So now, if we take the square root in both sides, we got the dimensional field. And this unit vector n means the unit vector of the any direction, random direction at the given time t. And that is the magnitude of the thermal field. And okay, let's check it. Let's check it. This part, maybe you can write down again. H square in left-hand side and 2 alpha kbt over gamma mu 0 ms delta v delta t. Okay, so let's move to h multiplied by gamma mu 0 ms. Sorry, mu 0 ms. Then this is the gamma mu 0 delta v delta t for 2 alpha kbt. Now we are talking about the dimension, so we don't need to care about the alpha. This is the dimensionless. And if you move the delta v in this side, delta V. So this is the mu0 ms multiply field is the Gman energy, actually energy per volume. So when you multiply delta V, this is the unit of energy. And this is the unit of energy also. So we can drop it. Okay. So the remaining is H delta gamma mu0 T. And as you know, if you move mu0 H gamma in left-hand side, this is the frequency unit. So this is 1 over T, right? So we just shows this complicated expression as a unit of the field. Unit of field of the ampere meter. So let's calculate the magnitude by the special number, a typical number. So we insert the 0.01 for the alpha and 300 Kelvin for the temperature with the Boltzmann constant and the gamma value and so on. And now we have this number. Every number is straightforward to insert. For the MS, we put the typical MS of the ferromagnetic material. But what's the delta V and delta T? In reality, when you think about this delta function, delta V, delta T is going to 0, right? So that means the magnitude of this thermal field is going to infinite. But in real life, delta T, delta V cannot be go to 0 because of the uncertainty principle. For example, delta T must have this relation because the uncertainty principle. The delta T, this is the energy. Delta E, delta T, V has such relation for the uncertainty principle. So delta T is 10 to minus 13 something. Okay. So this is the 0.1 picosec, right? Do you think is it a very, very small time scale? Maybe 10 years ago, 0.1 picosecond is really, really a short time. Nowadays, the femtosecond spectroscopy is very popular. So it's not that difficult to measure a few femtosecond something. That means not difficult means for some expert, not for me. If you have a proper instrument, you can do some such kind of fast physics, fast dynamics. But in a magnetism, this kind of time is very important to understand the many situation because of the spin dynamics we already learned is order of gigahertz something. So most of the important spin dynamics occurred order of below the nanosec, not the picosec. So for the magnetization dynamics, this is really, really short enough time. Okay, you know, this year's Nobel laureate got a Nobel Prize because of the invention or contribution for the attosec physics. Attosec is 10 to minus 18. So this time scale means if you have some propagating electromagnetic wave, this time scale is we cannot make one single wavelength, one frequency, less than this frequency. So actually, many physics textbooks assume some adiabatic assumption means the time something happens in within very, very short time or very, very long time. Otherwise, it's very complicated. But this attosecond physics, we can observe such kind of time scale physics, and we need modificate the many, many theory because of this time scale is very, very short. Okay? So always we assume if there's some perturbation, and then we can observe only the ground state. So we cannot see the real dynamics in many physics. But in magnetism, everything occurred in around nanosecond something. So we can easily observe such kind of behavior with the femtosecond laser of physics. But some physics requires more shorter time. So the attosecond laser open the way, observe such kind of short, very fast dynamics. That's the meaning of the low rate. Anyway, so the time scale in our spintronics, that is the very fast enough time. So the other way is it's difficult to going the more faster device than this limit. Okay. So if you insert delta t with this number, and for the delta v, I insert the 1 nanometer by 1 nanometer. So it's pretty small nanoparticle. Then we got the 2.5 Tesla magnitude. So that means such kind of large field can be applied within every this time interval for this volume. And that means if this kind of size field is applied, this size of particle pointing always this field direction, right? And this is the random. So 1 by 1 by 1 nanometer particle, they occur, they got some kind of field, order of 2 Tesla field for every this time. So the magnetization direction is pointing random direction every this time. So if you take a time average, what's the magnitude of this field, the magnetization? It's 0. That's the meaning of the superparameterization. What happens if you increase this by 10 by 10 by 10? Then this field magnitude is smaller than 10 to root 10, so it's about 30. So we got the effective field of the point, maybe less than 0.1 Tesla something. So it's moderate. If your particle has a large enough anisotropy energy, they can stay their own direction, even though there's some agitation. But if you shrink down your size of your particle, they are following this magnetic field direction. And yeah, if you are not the real magnetism guys, there's no feeling about how much large field of 2.5 Tesla, 2.4 Tesla. Actually, typical ferromagnetic material for the recording media, the anisotropy energy is usually order of Tesla. If you make a really large Tesla anisotropy energy, it's really hard to switching. So usually we played with less than Tesla of the anisotropy field. So this is large enough, but 0.1 Tesla is not that large. So we can keep the information for the 10 by 10 by 10. But what happens if you play with the thin films, 10 by 10 by 1 nano? Then it's just nano divided by 10, so 0.2 Tesla something. So it's really marginal. If you're making such kind of MNAM with such anisotropy energy, then the retention time is very limited. So this supermagnetic limitation is kind of bottleneck for the information storage application for the spintronics. Not only spintronics, but any kind of binary data storage systems. Anyway, so yeah, actually this kind of idea is, for example, the ferroelectric material, ferroelectric material. The detailed mathematical discussion is not the same, but the physical, the meaning of the ferroelectric material also has a kind of a tension temperature called also called the P temperature. So they actually, I believe, almost a similar thing happens for the ferroelectric one. So, right? Okay. And I just copied the some brief introduction of the Curie temperature or the temperature dependent pronunciation. It's same in a previous textbook, previous lecture note, very beginning part of this class. But I'm gonna just briefly review again. Anyway, so we are talking about the temperature. So the competition between the thermal energy, in other words, random field, and this competition between the exchange energy is kind of the definition of the Curie temperature. So exchange energy try to align the spins, and the thermal energy want to make the random motion of the spins. So these two energy compete each other. So this Curie-Weiss law is actually how they can compete each other and in what conditions the exchange energy is dominant and the ferromagnnetic alignment is occurred in a final temperature. That's the physical meaning of the Curie temperature. But to understand more deeply, we need the concept of the spin wave. Then spin wave concept is very important to understand, especially the excitation of the this, spin motions. Maybe I can give a lecture about the spin wave, maybe almost the end of this semester, if we have time. But before that, I'm gonna just briefly mention about the spin wave. Okay, so this is the review of the main field theory again. So in a random, in a ferromagnnetic material, the all spin direction are random. So average value is 0. But if you apply the finite magnetic field, there is non-zero average value because of the aligned spin has a lower energy, but because of the Zeeman energy. So this average value give us certain magnetic moment called the average value of magnetic moment is proportional to the each magnetic moment of each atoms and the Langevin function. And here the S is defined by the ratio between the magnetic energy and the thermal energy. And with this expression for the small s, small enough s means this means the temperature is high, then this Langevin function can be take the approximation. We obtain the linear approximation of the S over 3 and this line. And we can obtain the magnetic moment for the given condition. Okay. So we got the susceptibility of this amount. And this susceptibility shows the 1 over T temperature dependence. This is the paramagnetism. Okay. And if you think about the ferromagnetism, we introduce some kind of molecular field here, extramolecular field. With this hypothesis, we obtain the new susceptibility temperature dependence, and this means that when the temperature T is approached the Curie temperature, the susceptibility will be divergent, means the phase change. Okay, and there are some descriptions. Please remember that. And from this idea, we can obtain the Curie-Weiss law, the M-burst temperature dependence. It shows such kind of a curve. But the experimental data shows some over behavior looks fine, but there are finite deviation. So this deviation reason is we do some classical approach, and also we talking about only the random thermal motion, but the reality is we need consider some kind of excitation of the quality system. So this is what we call a spin wave. Yeah, nowadays many scientists talking about the spin wave and Magnon is the same meaning, but in more rigorously, spin wave and Magnon is a little bit different. The Magnon is quantization of the spin wave. So when we're talking about the electromagnetic wave, sometimes we are saying this is photon, but sometimes we are saying electromagnetic wave. But the real physical meaning is a little bit different. If we want to handle the electromagnetic wave as a particle, photon is easy to describe the property. But electromagnetic wave has sometimes wave nature. So yeah, if we are using the photon concept, somehow we can explain the wave nature, but it is more difficult. But between the spin wave and the magnon, they're a little bit different. When we are talking the electromagnetic wave, always we think about very well-defined electromagnetic wave. But when we are talking the spin wave, it's kind of just a propagation of the spins. But they cannot be described by the magnon. We need quantization. So yeah, it's maybe a little bit long story. So anyway, sometimes it's fine if you compute the spin wave with the magnon. Nobody care about that. And also, as you already mentioned, we need to care about the band theory to explain this data correctly. Anyway, so this is kind of remind. And so the effect of temperature is always important. And this superparamagnetism, let's consider again. Energy is the amount of the work. So please don't confuse energy per volume and the energy. When we the correct pronunciation of the energy per volume is energy density. But sometimes they are using just the terminology of the energy, but it's totally different physical quantity. It's like the mass and the density. Mass is the amount of the substance, but the density is the property of the materials, right? So don't confuse. So, for example, the NSP energy is the energy density unit. It's joule per meter cube unit. So, to make this energy, the energy density to the energy, we need to multiply the volume. So the energy barrier by the thermal energy, the energy is Ku multiplied by the volume. And actually this cavity at the room temperature there is no way we can control it. It's fixed value. Right? We have no idea, no way to avoid it. Only way is cooling down the system, but this is not practical. So if you consider the typical energy of the ferromagnetic material is order of 10 to 5, 10 to 6 joule meter cube. And if you certain number, we have a such relation here. R cube is the size of the magnetic material. And if R is order of 5 to 10 nanometer something, we got a 30, the 40 in this calculation. So 40 means this is the thermal data delta, thermal stability delta is the kind of limitation of the retention time. So we need at least this volume to maintain the information or the direction of the magnetisation for a long time. But some application, we don't need such kind of long retention time. For example, the random access memory. As you know, in a DRAM, the retention time of data is always only 60 microseconds something. So such kind of temporary memory, like cache memory, then we don't need such large retention time. In that case, we need only maybe 20 something is good enough. But anyway, but this is the really limit. If you only ways you have to increase the Ku or the volume because this is the fixed value. KBT is fixed value. There's no way you can alter. But as I said, if you increase the K, then it's the switching energy required. The switching is getting larger. This increase the energy consumption of the device. So the minimization of this and the size of the system is limited by this superfinite limit. This is bad news for the application, actually. yeah, here, especially for the instead of R Q, if we play with the thin films, the thickness is always order 1 nanometer something, 1 nanometer something. So we need certain size of the radius. Depends on this size, we got the delta of the this number. So if we have a small unaspecified energy, we have a small delta, so it's not easy to make the real system. Okay? But if we have this number, yeah, then we need more energy to write the information. Okay, and I should mention the superparametric once more. The image curve of the superparametric material is it actually looks like the parametric behavior because this superparametric is actually non-interacting molecular at the moment. So we can apply the parametric theory exactly to the superpara. But the difference is here. The susceptibility itself is actually the mathematical description is the same. But here the mu is different. Mu is, in a parametric approach, we talking about the molecular magnetic moment. But here mu is the magnetic moment of the parametric particle. So the order of magnitude of this mu is really large. Okay? So the image curve of this superparametric particle looks like just some approximation is the good approximation tangent, hyperbolic tangent. And this is applied for the low temperature limit and the high temperature limit each other. And yeah. And this detail behavior is not maybe not very important for many students, but this part is very important. This superparamagnetic material is very useful in many applications. As I said, the superparamagnetic itself is very harmful for the memory application. But the biomedical application, it plays very important role, especially in imaging using the MRI. They are using some constant agent. This made by the magnetic nanoparticle. In Korean word is 조영제. Have you ever heard about the 조영제? Is there anyone who took the MRI? Yeah. When you're taking this MRI imaging, they inject some kind of actually 조영제, the contrast agent. Then in your body, then this is the very small nanoparticle with the ferromagnetic materials, and they show some better contrast for this MRI imaging. So this is the very medically very important. And also, magnetic separation means there are many applications with superparametric material attached to some cells and moving the cells. Actually, this is the main theme of Professor Choi Kim in physics. And also, there are other application called target drug delivery. Means if there is some part of your body is abnormal, for example, cancer, then actually one of the way to treat the cancer is give us some very toxic chemicals to kill the cancer cells, but it's too toxic. So if you eat it, then other part of your body will be damaged. So this target drug delivery is they deliver this drug for the target point only. So the other part of your body is not affected of this kind of toxic medicine, but only this part cell can be damaged. So it's a very important approach to treatment of cancer. And also there are other one important thing is hyperthermia. Hyperthermia means it's kind of a heat treatment. If you send in large nanoparticle for example, some cancer part, and then give us some kind of RF in outside, then this ferroelectric material observe this RF for the certain frequency by the resonance, then they generate heat. and this heat will kill the cancer cells. So this kind of approach, there are many research, related research even in the disease. But for this application, the important thing is making very uniform size and well-aligned parametric materials, the super parametric materials. So this kind of super parametric material can be made by some chemical treatment. So it's actually a little bit far from the spintronics, but actually it's also very important application of the magnetism. Okay. So today I'm talking about the superparamagnetism, and you may encounter this superparamagnetism in some applications. And also, I'm sure you must encounter this kind of temperature effect in any kind of application in a real engineering field. So in the next class, I'm gonna explain the Aranas real switching, and yeah, so far I explained the effect of the temperature. And now, how we can analysis this effect of temperature by measuring the switching mechanism. Okay, so let's finish this lecture here, and see you next Monday. Okay.